some start.
So now I am sure that after discussions in last few sessions, we had become familiar with the circuit analysis, wherein we study the behavior of the circuits in which reactive elements are present and which are subjected to some input source. It may be voltage source or it may be current source. It may be AC source or it may be DC source. One important point which is to be mentioned is that it needs to be applied by a switch, because we start the system at some known time instant. We cannot have any system in practice which has been there since minus infinity period. Therefore, that is the transition from where the transient response begins. So, the two chapters, that is the first is Kirchhoff's, that is the general circuit analysis, and second is the transient analysis, are comfortably over. One point requires to mention that we shall finish today, so that we are comfortable through the first two chapters. You can view the syllabus on intranet, or I will supply it to you its soft copy. We had from day 1 till now had presumed that an entity called as a voltage source. We were working on an entity called as a voltage source. So that entity, which is a voltage source, was being considered by us that it was having a symbol like this, and we used to write 5 volts. This is the entity called as a voltage source. What does it reflect? What does it mean for me? How does it work? The idea is very clear that till this point of time, we were presuming that this is a unit which always supplies, I insist on the word always, which always supplies a voltage of 5 volts across it. A voltage of 5 volts across it. My stress on the word always is important. Roll number 20. 20. My insistence on the word always is very much important. Now, let us try to see what problems may occur in practice, and let us try to find out what is the solution for that. In this, we will come across a very repeatedly referred and less understood theme of 0 into infinity. On that we shall have a separate talk some other time. We will not be spending time in the present flow now. So let us now have a resistance connected across it. And let us say resistance of 100 ohms. Let us say resistance of 100 ohms. So how much current would be required? How much current will flow? How much current will be supplied by the source? Obviously 5 milliamps, right? Or what it is? It is 50 milliamps. 5000 millivolts upon 100, 50 milliamps. Then let us have a very simple, I am trying to simplify the discussion. This much simple may not be even necessary, but we shall take a view that it should be simplified so that there should not be any doubt in anybody's mind. So if we decide to reduce this resistance, for that purpose we will have a potentiometer, a rheostat, which you are aware of. And if you start moving rheostat on this side, what will happen? The resistance will go on decreasing further and further. So what is this limit? So if resistance becomes 1 ohm, current would be 5 amperes. 0.1 ohm, 50 amperes. Like that, as resistance goes on reducing, it will demand, the system, the circuit will demand very heavy current. Say 0.0001 ohm, maybe 50,000 amperes. So do you think that this is something which can be implemented? Just by very common sense we have to answer. We need not be very much scientific. So we find that it would be difficult, may not be impossible, we can conclude right now. It would be difficult to have a voltage source which would be supplying this much amount of current. Such a voltage source we cannot get. The reasons, we are not studying any what we can say electrochemistry in detail, but we may have some information. Say a electrochemical cell, what is the voltage or actually the EMF of the electrochemical cell? It is a property of the electrolyte and electrode, and it is fixed. So the electrolyte electrode combination has got its own EMF. Where you are looking at some electrochemical cell there. Then current is what? Current is the rate, and rate of flow. To be more particular, current is time rate. Current is time rate. Rate of flow of electrons. So if we have analogy of electrical engineering and chemical engineering, then this is which is time rate must also be proportional to some time rate on the chemical side. So what happens in an electrochemical cell? In an electrochemical cell, chemical reaction takes place, and there is a rate of chemical reaction. Rate of chemical reactions depends on what? The concentration of the electrolyte. So ultimately the current is proportional to the rate of chemical reaction. The rate of chemical reaction is proportional to the concentration of the electrolyte. Then can we increase the concentration of electrolyte infinitely? What is the reason? Because there is the concept of saturated electrolyte. Even if you go on adding the salt cannot be absorbed by the solution beyond a limit. So once the electrolyte saturates, the rate of chemical reaction cannot be increased beyond a certain limit, and therefore actually the rate of chemical reaction depends on the volume as well as the concentration. So there is a limit for a given cell to supply the current. Depending upon the size, that limit may vary. Therefore, our assumption of a constant voltage source is completely wrong. We cannot get a constant voltage source, because the constant voltage source requires to supply fixed voltage across it always. So even if an infinite current is demanded, it has to supply fixed voltage. That it cannot do. Therefore, this is called as an ideal constant voltage source cannot be available in practice. Therefore, we get a term called as a practical constant voltage source. It is no longer a constant voltage source now. Ideal voltage source is a constant voltage source, and practical voltage source comes up with some voltage given by it and a maximum limit on the current which it can supply. Then how can you model that voltage source? The voltage source is, so there is a voltage source which can supply 5 volts, and and voltage across it which can supply. It doesn't mean that it will always supply. And it can allow a maximum current of what we can say 200 milliamps. When maximum current is there means a voltage source of 5 volts which has ability to supply maximum current of 200 milliamperes can be modeled as an ideal constant voltage source plus something. Are you getting me? Ideal constant voltage source is not there in practice, it is there in the model. So a practical source of 5 volts which has got a maximum limit of 200 milliamperes on the current which it can supply can be modeled as an ideal constant voltage source of 5 volts plus something. What is that plus? What a plus can be? So it is ideal source. Plus something. Plus something should be that maximum current can supply is 200 milliamperes. So if I short it, how much current will flow? 200 milliamps. So for 5 volts, this current is 200 milliamp. So what resistance must be there in the system? 5 volts upon 200. It is 5000 upon 200. That is 50 upon 2. That is 25. So this is the voltage source available to me. What is available to me is this is the practical voltage source of 5 volts. Practical voltage source of 5 volt is considered to be a combination of an ideal voltage source and a resistor. It can't be separated out. It cannot be separated out. Right? Otherwise, you will ask, no, it's a combination of ideal voltage source and resistance. Then separate it out. It is just like, suppose if a lively human body is a combination of what? A lively human body is a combination of a human body and livelihood. A lively human body is a combination of human body and livelihood. Then is it possible for you to separate it out? You can get a human body which is dead, but you can't separate out the livelihood. So a practical voltage source is a combination of an ideal voltage source and a resistance. You can get the resistance independently, but you cannot get this independently. So this is an indivisible combination. So from this combination, this part can't be extracted out. Similarly, as from the lively human body, you cannot extract out livelihood separately. In the same way, from a practical voltage source, you cannot separate out, you cannot bring out the ideal voltage source outside. So it's a indivisible combination. Right? This is a practical voltage source.
Sir, then what we use in Proteus and all, are they practical or voltage sources?
So in Proteus, the thing is that it doesn't have to supply current at all. So it can be an ideal voltage source. All problems which you have solved are based on ideal voltage sources. You might be performing some practicals in the lab. There you are having a power supply. Its voltage is constant. What is that then? Is it a practical voltage source or ideal voltage source? It is neither a practical nor an ideal voltage source. It's a regulated power supply, wherein you may set it 5 volts, 10 volts and connect resistor, current will change, voltage will remain constant. It's a regulated power supply. Regulated power supply is very innovative and important design of a human being, because what happens actually now, for if we plot this axis and I on this axis. For a practical voltage source, what should be the graph? Sorry, for ideal voltage, what should be the graph? For ideal constant voltage source, V is voltage across the source and I is current supplied by the source. V is voltage across the source and I is current supplied by the source. So what should be the graph for this? For ideal voltage, what should be the graph? Straight line is not the answer because all graphs are straight lines.
Passing through origin.
Passing through origin, how? For ideal constant voltage source, what nonsense you are answering?
Straight line
Parallel to
x-axis.
x-axis. It has got some fixed voltage, so it will supply same voltage throughout, irrespective of the current. What would be the graph for practical voltage source? Is this. If no current is drawn, what is voltage across it? So it is, if ideal voltage source, let us say 5 volts. Now practical voltage source 5 volts. So when no current is there is no voltage across it. So it is 5. And when current flows, there will be voltage drop. And when the current is 200 milliamps, what is the voltage across it? Before answering, think something. You are a sensible student. This is A and B. So if I short this, how much current will flow? 200 milliamps. What is the voltage VAB? 5 volts. Do you have some sense? When we short this, entire drop 200 milliamps into 25, entire drop across this. So it will be 0. And then the practical voltage source is a straight line like this. Practical voltage source is a straight line like this. Now, regulated power supply. Regulated power supply is designed by using a practical voltage source. Suppose if I have practical voltage source of 5 volts, using that I can design a regulated voltage source of 2 volts in such a way that this is 2 volts. So up to this limit it will behave like this. A regulated power supply is a power supply which behaves as, now what is the problem with practical voltage source? I wanted ideal voltage source. I want it like this. I can't get this. I get this. This I don't want. So a regulated power supply is a design which behaves like an ideal voltage source, but only up to a certain limit and not beyond that. So the problem with me was there is a maximum limit on the current sourcing, and because of that an inherent internal impedance, this is called as internal impedance of the voltage source. A practical voltage source comes with Vs and Rs. A practical voltage source can be thought to be comprised of an ideal voltage source Vs and an internal resistance Rs. This I cannot do away with. This will always be there. Because of this, what problem occurs? The graph starts falling down right from this instant itself. In that case, what I can design using a 5 volt voltage source, this Rs and this some variable R, I can construct this to be a 2 volt regulated voltage source. What I do? Based on this, there will be some load resistance. This I will apply some load. I connect a voltmeter here. I observe the voltmeter and I adjust this R. I observe the voltmeter. Suppose if this resistance reduces, the voltage will drop. I will reduce this resistance. So that voltage will again increase. So, and instead of me, there is a mathematical circuit. How can we construct a regulated voltage source and a practical voltage source plus a variable resistor and feedback? These are the output terminals. These are the output terminals of a regulated power supply of 2 volts. So what I do? Between that I have the voltmeter. I have my eyes are at the voltmeter. My hand is at the knob. My hand is at the knob. What happens? If I find that the voltage is increasing, then I increase the resistor to reduce the voltage. If I see that the voltage is reducing, then I decrease the resistor so as to increase the voltage. But there is a limit to me. Why there is a limit for me? Because if I go on reducing the resistor, voltage will drop down. So as to increase the voltage, I have to reduce this resistor. But I can reduce this resistor only up to 0. I can't have negative resistance. So when I reduce voltage, this resistor up to 0, beyond that I am helpless. Because what I am doing, I am ensuring that this resistance I am ensuring such that 2 volts are required. But a limit is reached where this resistance reduces further. I can reduce this resistance up to 0 only. So in no way this effective resistance can be reduced to a value less than Rs. So I cannot reduce this resistance below Rs. Therefore after that the voltage starts dropping down. After that voltage starts dropping down. This is the difference between an ideal source, an ideal voltage source, a practical voltage source and a regulated voltage source. So the idea is clear. An ideal voltage source is that source which will always maintain a fixed voltage across it. An ideal voltage source is that voltage source which will always maintain a fixed voltage across it. Such a voltage source cannot exist in practice, because if ever it exists in practice, it will be required to supply a very heavy current for small resistance loads which it cannot supply. Because wherever you may go, by whatever method you may generate the voltage, there is a time equivalent in every process. Therefore that process cannot be expedited in time beyond a certain limit. In case of electrochemical, it is chemical reaction, and because of that every voltage source has got a figure called as maximum current which it can supply, and therefore every voltage source which is there in practice, may it be an electrochemical cell, may it be a DC voltage generator, DC generator, or may it be photovoltaic cell, may it be thermocouple, all kinds of voltage sources which are available in practice are suffering from or are possessing an internal resistance which is unavoidable, and therefore a practical voltage source is a combination of an ideal voltage source and internal resistor. Because of that internal resistance, the VI characteristic of a practical voltage source becomes like this. And this is something which is very poor. This is something which is very poor. I wanted this, I get this. And this is very poor in the sense, we may give a very small application. Suppose if I am having a DC motor. For a DC motor, the speed is proportional to voltage. Then you are having one source on which you are connected one motor, one lamp, some other application. So what will happen? Suppose if you put on the lamp, the voltage of the voltage source will reduce. That will affect the speed of the motor. Suppose you put off the lamp, speed will increase. Like that. So what we want, ideally we should have this. We cannot get this. We get this. Therefore, regulated power supply is considered, human being designs many applications. Out of these applications, I consider regulated power supply to be one of very intelligent designs, very innovative designs done by human being, because it uses a means what regulated power supply does. Regulated voltage source. We have three sources now: ideal voltage source, practical voltage source, and a regulated voltage source. A regulated voltage source behaves like an ideal voltage source up to a certain limit. Regulated voltage source uses a practical voltage source and behaves like an ideal voltage source up to a certain limit. Regulated voltage source is considered to be one of the very innovative and critical intelligent designs, because from practical voltage source, or it makes a practical voltage source to behave like an ideal voltage source. Means ideal voltage source is unachievable, impossible. It makes practical voltage source to behave like ideal, maybe within some limits. At least within some limits, it makes him to behave like ideal. I have a very significant example for it, which is one from very ancient history and one from very recent history. As regards to leadership, if we may not be competent to evaluate, but as a student of history, every individual has to evaluate. If we evaluate various leaderships, then we will find Lord Ram and Mahatma Gandhi are considered to be exceptional leaders. Can you, based on my examples, what exceptional quality do they exhibit? It is just like when a question paper is given to you, in the answer book, you may be coming across some students who are not so strong in studies, but they are having the methodical things they do very neatly. They get the answer book first, then they get a scale, draw lines in the answer book, put numbers neatly in letters and in numbers, then they turn on the first page, then the question paper comes to them, and what the first thing they do is write down question 1. They rewrite the question again. What exceptional qualities these two leaders exhibit now? Why these two are considered to be exceptional leaders? What? As regards to Lord Ram, he is not attributable to non-violence. They forced others to be leaders. No. Now Lord Ramchandra, you may not get the exact significance. The leadership can be evaluated on 2 counts. Number 1, building of the Setu from India to Sri Lanka is one act, and leading the freedom struggle is another act. So leadership of Lord Ram is to be evaluated on the building of the Setu, and leadership of Mahatma Gandhi is evaluated on leading the freedom struggle. In that, now what is the exceptional? Suppose if we appoint somebody from your class as class representative, he is supposed to lead the class and they achieve something. Do you attribute the success to leadership? Yes or no? Not necessarily. From this building of Ram Setu and leading the freedom struggle, what is the exception there? No, that is not exception. Giving importance to each and everybody is something which can be described in the textbook. Yes, these are the qualities required by a leader. What is exceptional there? Unite it again. No, it's okay. No doubt that these are the general liabilities, but not exceptional. It is this example I am giving because it is having very much relevance with the regulated voltage source. So from that point at least you can think what it is. Regulated voltage source is considered to be very intelligent and innovative design because it makes practical voltage source to work like an ideal voltage source at least for some time. So the success of these two leaders is considered to be exceptional because they made their very much normal followers to achieve exceptional things. The followers were quite normal and general in nature. It is the monkeys who built, it is said that they built up the Setu. And a very common illiterate Indian participated in the freedom struggle. So making a practical and a very general thing like an ideal, at least for some time, is considered to be innovative design. So these two leaders are exceptional in that sense. There can be debate on whether it was an appropriate method or not, and it is very easy for us to criticize and evaluate. But everybody has to admit that these qualities are exceptional and there can be no match in the history. Leading a mob which does not understand, for which does not fully understand what is the purpose for which they are doing something and getting the task done. Similar means making a general thing or from general people achieving something which is very special. Making general thing looking like an ideal thing. So making practical thing looking like an ideal thing, making general thing looking like a special thing is being done. Therefore, regulated voltage source is a very interesting design. So we get a practical voltage source and we have a regulation. I think that you might not have fully understood what is regulation, on which we may throw some further light. Okay. We may do it by design itself. Design a 5-volt regulated source. Design a 5-volt regulated source from a practical voltage source. Design a 5-volt regulated voltage source from a practical voltage source of 10 volts and 50 ohms. You may have small teamwork within the desk only. The teamwork is not expected to be that large. So small teams of 2. Teamwork is optional and not compulsory. Let's pause this. Suppose if now the theme is very clear that I have a constant effective voltage source of 10 volts and 50 ohms, right? Now I will be adding a series resistance which is variable now. But there is a problem. The problem is now like this. The problem is if it is open circuit, how much voltage will be here? So I want a 5 volt regular voltage source characteristic. If this is 10, 5. It should be like this. This is my original 10 volt characteristic. So for even no load, now there should not be. Now what is that? What will be voltage here? 10 volt. That I don't want. I want this to give 5 volts for zero current. It should continue till a point. Beyond that it can't continue. So how I can do that? So only a series resistance will not be enough. I have to add a dummy load resistance, and everything would be inside. Everything would be inside, so that I have to add a dummy load. I have to add a dummy load. Means that even if a no load condition is avoided. No load condition is avoided. Now how much value I can add now? This I will add some fixed value, and this I will keep variable. So how I can achieve that? Let us have, we can start with brute force method. Suppose if I have it as 10,000 ohms, 10 kilo ohms. I have this as 10 kilo ohms. And I also have this as 10 kilo ohms. Variable. Variable. So now what I will do, at no load, I will adjust it to be 9950. I will adjust this to be 9950. So 9950, 50 ohms, there would be 5 ohms. Now if I connect some resistance like of say 100K. So what will happen? 100K and 10K parallel will come. So effectively it would be something like 9K also. So when I connect this, what will happen? Voltage will drop down. So as to adjust, I will use this. So what I can have, I can presume myself inside this voltage source. I can have voltmeter, and so my eyes are at the voltmeter and my hand is at the knob. So when task is very simple, if you find that voltage falls, turn knob on the left side. Means voltage, when voltage will fall? When this resistance becomes small. So turn the knob on the left side, reduce the resistance. So in order voltage will increase. If you find the voltage increases, turn the knob on the right side so as to reduce the voltage. So if this resistance becomes 50 ohms, what will happen? If this resistance becomes 50 ohms, what is going to happen? Or say 60 ohms. If this becomes 60 ohms, what will happen? 60 parallel 10K would be something. It will be reducing that. So it will be going just near 0. So 55 again reducing. So there would be some load for which this will become 0. That load for which this is 50 and the combination of this and this becomes 50. So it will be something like 50 point or 51 ohm or so. So from 51 ohm or so, you will find that this combination becomes 50. This is 50. So 5 volts. Suppose if this becomes 40 ohms, what will happen? This is 0. It can be made negative. So a point will reach here. A point will reach here. That beyond that, it can't continue. It will fall in this way. Means in any case, it cannot source 10 volt. That is 10,000 millivolts upon 50. That is 1000 upon 5. Means in any case, a current more than 200 milliamperes can be supplied. It can't supply. So this is the regulatory voltage source consisting of a series resistance which is to be controlled, and why this is needed? Very high parallel resistance is needed. This is needed because if we don't put that, for no load condition our element will fail. For no load condition our element will fail. In order to see that the element succeeds, the resistance. Is it right?